So yesterday we talked about the principles of satellite motion, and that if something is going to orbit something else, the centripetal force is going to be provided by the force of gravity, okay? And not what we call little fg, but big Fg. Okay, so if you hear me use those terms, little fg is m times g. Okay, big Fg is Newton's universal law of gravitation. Big G times mass 1 times mass 2 over r squared. Okay, and then obviously mv squared over r. Okay, we also looked at if a question asks for period of rotation, okay, or asks for radius and gives you period, then you might have to substitute in for v because you wouldn't have it. Okay, and if we have to do that, we take the formula for v, 2 pi r over t. We plug it in for v, but v is squared, so we have to square the formula. 4 pi squared times r squared over t squared, and we just plug that into the formula, and we end up with this. m 4 pi squared times r squared over t squared times r, but the r on the bottom cancels that one, okay, and we're left with that once it's all substituted in, okay, big G, m1, m2 over r squared. Other thing to remember, in both instances, one of the m's is on both sides. Which one? Right, the orbiting mass is the one that is on both sides because the m in mv squared over r is the mass moving in the circle. Okay, that mass is on both sides and thus it cancels. That means then that the speed and period of a satellite is not affected by the satellite's mass. Okay, that's the quick review from yesterday. Let's try 1 and 2. First one's only asking for orbital speeds, the easier of the two. Second one is asking for orbital period. Okay, and we'll require the substitution, which I am now going to erase so that you can use it. Because I'm not trying. All right, so our first one, the first two steps are on the board here. Okay, obviously gravity is providing the centripetal force and we're looking for the orbital speed, but there is a trick here, and that is that one of those key words we talked about yesterday is in this question, and it says that it is orbiting at a height. Where is height measured from? Height's measured from the surface. Okay, separation distance or orbital radius are measured center to center, but those key words are height, altitude, and above the surface. This one uses height, so we know that we have to add what to this number?
The radius.
The radius of the Earth, right. Okay, so in order to get the true orbital radius, we've got to go 6.37 times 10 to the 6 plus 359,200 meters, because it has to be in meters. Okay. All right, so, oh, I forgot to start my calculator. Okay, so we will have 6.37 E6 plus 359,200. All right, so our actual orbital radius is 6.7292 times 10 to the 6 meters. Okay, so that is low Earth orbit. That's where the International Space Station is. Okay, and now that we have the radius, now we can solve for v. So in order to do that manipulation, I'm going to multiply both sides by r. When I do that, the squared is going to cancel. The mass of the satellite is going to cancel. And then I'm going to square root. So I will have v equals the square root of big G times what mass?
Earth's mass.
Earth's mass. Okay, over r. Right, so when we plug in our numbers, that's going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 6.7292 times 10 to the 6. Okay, so plugging that in obviously is a little bit hairy, right? But we will have 6.67 e negative 11, 5.98 e24, okay, divided by that number there, squared, that's definitely not fast enough. I messed something up somewhere.
I think you squared root, you squared root the radius.
That's the radius there, I just put it back in. Did I accidentally square it?
I think so.
Oh, okay. I did, that's exactly what I did, yeah. And I can't go back. So now I get to type the whole thing in again. Okay, you're absolutely right though, that is totally what I did. 6.67 e negative 11. Divided by that number, just that number this time, Coder.
Curly.
Oh, I got a curly bracket. Why did I get a curly bracket? Oh, I had the second function. This is the answer. Right here. That one. I don't need to prove it. Yeah.
Aren't there 4 significant digits?
There would be, yes, sorry, 4 significant digits, absolutely, because that number there is measured. One of many mistakes in this book. Mhm. All right, how many people have done number 2? Okay, I'll give you a couple more minutes on number 2. Okay, looking for the orbital period on that one. And I will try not to screw up the calculator this time. Okay, so number 2 is going to start out same way, FC equals FG, but now we're going to have to do that substitution because our givens are different. First off, we know it's orbiting Earth, so mass of the Earth is going to be one of our givens, and then it gives us an altitude of 114,593 kilometers, which still needs to get converted to meters and then added to the Earth's radius. Okay, so we're going to have that the actual radius here is going to be 6.37 E6. Okay, so radius of the Earth plus 114,593 with 3 more zeros behind it will make it meters. Okay, and that will give us an orbital radius of that number, 1.20963 times 10 to the 8. I'm not writing it all down. I'll keep it in the calculator. Okay, so there's my orbital radius. Okay, and now I need to do this. mv squared over r equals big G times mass of the Earth times the mass of the satellite, which is also over here, over the orbital radius, center to center. Now, I don't have v, and I have r, but I'm going to substitute in that formula. So I'm going to have 4 pi squared r squared over t squared, and I'm going to put that in here for v. All right, so when I do that, okay, obviously the mass of the satellite is going to cancel because it's on both sides. This squared here is going to cancel that r down there, and I'll be left with this. Now I can manipulate to find the orbital period. So I'm going to bring orbital period over here by multiplying both sides by it. Okay, and I'm going to get rid of the mass of the satellite. That squared is gone. Okay, that's gone. And I'm going to bring r squared over here. What's r squared times r? R cubed. Okay, and then I'm going to divide both sides by big G times the mass of the Earth to get that over here. And that will leave me with t squared. Okay, I need to get the just t, so I'm going to have the square root of 4 pi squared times 1.2 times 10 to the 8 with all the decimals in it, cubed, divided by big G times the mass of the Earth. Okay, is this likely to be a large number? Okay, is that all right? It is because it's in seconds, exactly. Okay, so we're going to have 4 pi squared times that number there, cubed. That's the top, that's a big number, okay, divided by the bottom, which will be, whoops, button. Okay, so I get 4.19 times 10 to the 5 seconds. Okay, that would be 116 hours. Okay, this thing is very, very far from the Earth because it has to be. It has to be outside of our like Van Allen belts and magnetic field and all of that so that its delicate instruments can detect things not interfered with by Earth. Okay, all right, how are we feeling about those?
How many sig digs would there actually be?
For this one here, there would be 6. Yeah, I didn't do it right either, but yeah, that's again one of the things that this book doesn't do well. Okay, in addition to having like, well, a booklet worth of corrections. I kid you not. When we first bought these books, when they first came out, the textbook like this big, and we're going through it, and we're like, okay, that's wrong, that's wrong, that's wrong, that's wrong, that's wrong, and we're like, there are a ton of mistakes in this book. Like, we're sending it back. Like, that's okay. We're sending out a corrections booklet. It only costs $20. And we're like, no, it doesn't cost $20. That seems like an issue, not an issue. You made a whole bunch of mistakes. Yeah. Then in the end, they reprinted all of them, all the textbooks. Peer editing, good thing. All right, I want to work on a couple more of these because we've got a short class today. Okay, a couple more satellite questions. Monday we're going to do Tuesday we're going to do gravitational field strength. Wednesday, our gravitation assignment. Thursday will be our unit exam review, or maybe I'll flip those, maybe it'll be Wednesday. And then Friday, we'll start the next unit. Okay, and your unit exam is Monday the 29th. All right, so in your digital workbook are some questions on satellite motion, and there's one on gravitation that I actually want to start with. That's so weird. Okay.
No. It's really
You can play that game. I win. Ah, except that picture keeps going. I just want to go home. Okay. Let's do it this way. You opened the wrong one. Okay. I'll win eventually. I'm gonna stop. Question number 11 in the gravitation one. Come back in here. Okay, so it's the 3 objects, kind of like Earth, Moon, and Sun. Question like that. Okay, I want you to do that one. And let's say 2, 4, and 5. 2, 4, and 5 from the satellites, and number 11 from the other one.